My fellow electrical engineering students, this is a crash course in Semiconductors 101. First thing I will be talking about is diodes, because they are fundamental before we understand BJTs and FETs or other transistors. Diodes are semiconductor devices designed to only allow current to operate in one direction. A diode consists of a P and an N region, and they are called as such because the N region is more negative than the P region. And this is achieved by doping the P region with trivalent impurities, meaning there are fewer electrons than silicon, which has 4, it's quadrivalent. And the N side with pentavalent impurities, meaning it is more so negative. Now, since silicon has a crystalline lattice structure, it is neither a conductor nor is it an insulator in the default state. By doping silicon in P and N, what we create is a slightly negative wafer of silicon, slightly positive side of the wafer. Now, when we form this sort of PN sandwich, what happens automatically, naturally, and by default, if you think about it, you've got a positive side and a negative side, right? And in the middle, it will create a diffusion layer, because the middle will be slightly negative as compared to the positive side, and slightly positive as compared to the negative side. Now, we use conventional current, so the idea that holes are charge carriers is pretty stupid, but it works, so I'm going to stick with that and not go into electron flow, because as we realized in another lecture by a prof, if you switch between electron flow and conventional current, it just gets confusing. So think of protons, which are just H plus if you know some chemistry. Think of them as holes or positive charge carriers, because we assume that charge is positive and it flows from the positive to the negative as per conventional current. So as electrons, following this right here, as electrons go through the depletion region and to the P side, this potential barrier is created. Now, it takes 0.7 volts to create and get past this barrier potential. So what this means is, as this diffusion region is being created, we apply electricity to it. It needs 0.7 volts to cross and to completely become conducting in the correct direction. Or I'm going this way because of electron flow, but that way in terms of conventional current. So essentially, once we have forward biased and past the barrier potential, which is 0.7 for anything silicon, it's 0.3 for germanium in case they throw a trick in there somewhere, but no one uses germanium anymore. Now, what happens in this case is, as we are moving these electrons, or sorry, we are moving the holes and the electrons as a result, wink wink, the forward bias decreases this depletion region size, and all of a sudden holes are able to jump, positive charge carriers are able to jump, and we have current flowing through the diode. Alright, in reverse bias for a regular diode, all reverse bias is if I have a power source connected, and we're still using in conventional current right now, if I have a power source connected to the cathode, positive side, and an anode connected here, what you will see is, sorry, I apologize. If you had positive side connected here, negative side connected here, what would happen is eventually in forward bias you get rid of the entire depletion. You pass the barrier potential, meaning there's no depletion region, or it narrows very much so, and you're passing current. In reverse bias, if you were to hook it up the other way around so that it looked a little something like this, ignore that it's a Zener, then what you would be doing is you'd be increasing the depletion region until at least you force so much voltage through it that you broke it down. Now, regular diodes compared to the Zener diodes, the big difference in terms of physics and construction is that they are lower doped. Takes less impurities, trivalent and pentavalent, for the construction of the P and N substrates in a regular diode. Now, a Zener diode is very highly doped, and we can follow from just logic. If we highly dope the P region and the N region, so this is the P region, this is the N region, I didn't label it, but this is the anode, this is the cathode, just the same way. If we heavily dope both regions, right, compared to either side, there will be very small room right there. It's already a narrow depletion region, and if you remember from what I said about diodes and how they work in forward bias, the charge that we apply to them decreases the depletion region before the charge can go through. And of course I am talking about Zener diodes operating in reverse. In forward bias they operate just like a regular diode. So when we apply voltage to a Zener and we reach a Zener effect voltage, one of our professors has always referred to it as breakdown voltage. That's a little bit wrong, because the breakdown of a Zener diode is very different from the Zener effect. So because of this very narrow depletion region, we're able to force current in the wrong direction if we apply enough of it. And that amount is the the VZ, the Zener voltage, as I and most of the internet and most of the world would call it. The VBR of a Zener diode is actually most commonly scientifically known as the avalanche voltage. The avalanche voltage is kind of the same as reverse biasing the shit out of a regular diode and pushing so much voltage through that you just burn it open. So, to review, P and N type substrates are created by doping silicon. We use things such as antimony, which is a very bad poison. Don't ever eat any of it. And that is pentavalent, and that would be in the N type. We use phosphorus or other trivalent atoms to create the P-type substrate. In silicon, the barrier potential, that's why you'll get 0.7 on all these labs, or somewhere very close to it, depending on instrumentation error or just a shitty diode or whatever. 0.7 is the barrier potential for silicon diodes. Anything silicon, really, even transistors, and that's going to be the next video. And 0.3 for germanium, but I left it off this board. The reason Zeners are able to work in reverse is because there is a higher level of doping, which creates a much narrower depletion region, which requires a breakdown potential. It is a breakdown potential in regular diode terms, which requires a potential in the reverse that can push the current in the wrong direction before this avalanche breakdown is achieved. Now, once you achieve the avalanche breakdown on a Zener diode, it's just like reaching the breakdown on a regular diode. You've just burnt it open. Anyways, I hope that helped. If there are any questions, comments, etc., I know I learn when I teach, so please let me know. Anyways, until next time, this has been Struggles with Electrical Engineering with Sharky Shark of Promethean Enterprises.